Muhammad, and this is another video under the moment distribution method. We're going to talk today about the basic concept of moment distribution through a very simple example that is going to show us how we can work with this method. Okay, now let's assume that we have this. We are going to show the concept using an example. And this example, as you can see, it is 3 spans, okay, 3 spans beam. It is fixed at point A and point D, and at point B and C there is roller under them. So this means that they are, these point B and point C, they are free to rotate. However, point A and point D, they are not, okay. And another point is point B free to rotate means that, and even that it has a hinge here or a roller, this means that the just to the right and just to the left of this point there is moment. So this means that as if the point here, this here, as if it is, there is moment that is going to be developed here and moment is going to be developed here, as if there is a fixation here and a fixation here, okay. So do not mix it up with, or do not be confused with having a roller. Roller means that it is, the rotation is allowed. But rotation does not mean that there is no moment will be developed. No, moment will be developed also. Okay? So there is theta that is going to be developed, and there is moment here. So what is the meaning of moment here? There is as if there is continuity. This means that as if this span, as if it is fixed, and this span is as if it is fixed, okay, similar to this span also, okay. So take care of this 3 points here. The span seems to be like they are equal, the first 2 spans. However, the third one is 15. Okay, we will use moment distribution table in order to solve it. We are going to make a table underneath each span to make our calculation better, because we are going to use everything in this table, okay. So, and we are going to put some factors here and so on. So we are going to use tables. Only for the information, EI is constant for all of them. So all of the members, they are having constant inertia, EI, and the values of E and I are given for us. We have only distributed load on the first span AB, concentrated load in the middle for the middle span BC, and no loads in this member. Let's go back here and have it, yes, here. So here this is no loading, and we have only loading here and here in this span, okay. Okay, now let's go and see what is the table that we're going to use, okay, through this example. So we are going to see this is the table. Do not worry about the numbers here. I'm going to explain it in detail. Do not worry. Just I want you to see this is the ultimate table that you're going to have at the end. So for each member, we're going to have like different column for each end member. So this end is going to be having this column. This end here, we're going to have to find that this is the column related to it. Sorry for this here. And this end, this column, and this end, it is going to be here. Similar for this, another column here and another column here. How many columns? 1, 2, 3. There are 6, which means that we have 3 spans and 2 end moments, 2 ends for each span. So we have 6 columns for our table. 6 columns for our table. Okay, so this means that we are having our table based on the numbers of the spans that we have. Okay, now let's start with the first. Let's put first things first. The first thing is, the first step is in analysis is, the first step in analysis is to calculate distribution factor. So you should start with distribution factor at those joints of the structure that are free to rotate. So we said before that we have 2 joints that are free to rotate, which is joint B and joint C. So for A and D, they are fixed, so we have no choice here. They are not. As long as there is joints that are free to rotate, this means that they have, yes, like relative, or there is a kind of distribution factor that is going to be developed. What is the meaning of distribution factor? Yes, it is the ratio between the relative bending stiffness between the element or the member that we are considering with respect to all bending stiffnesses for the joint, for all other spans framing into the same joint, right? So we need to calculate it first. So here we have B, which means that joint B, if we say this is joint B, there are two members are framing into it. This member and this member. This one is BC and this one it is BA. So we have, for joint B, we have two members. Okay, each member, it should have its own distribution factor. Okay, so let's calculate the distribution factor for member BA and for member BC. Okay, now let's have this, the distribution factor at joint B. We are going to call it DF. So DFAB, BA, it is BA, this span. It is going to equal, from the definition, go back to the previous video and you are going to understand what is the meaning of the distribution factor. So the relative bending stiffness of member BA over the summation of relative bending stiffnesses of all members framing into the same joint. So we have KBA, which is the same, because this member is one of the members framing into BA, and another member which is BC. So we have KBC here. So what is the meaning of K? Relative bending stiffness. Relative. So we are going to use what? Yes, I over L, the short form, which is I over L if the far end is fixed. Let's go to BA. What is the far end here? Exactly, it is fixed. So we are going to say I over L. L is 20 from here. So what is KBA? It is the same, I over 20. So we have here, this is I over 20. And the other term in the denominator is KBC. KBC. So what is the far end? It is fixed. Yes, do not think about it as roller. As I said, it is free to rotate, but there's bending moment is going to be developed. So the far end here is fixed, and we have the length 20. Then we're going to have it also to be I over L, which is 20. So the denominator is going to be I over L plus I over L. So it is going to be 2I over L. And in the numerator, it is going to be I over L, which is for member BA. This would give us 0.5. Let's calculate distribution factor for BC, which is BC. There are two ways for the calculation of the distribution factor for this member. First one is the easiest one, which is, do you remember that when I said before that the summation of the distribution factors, DFS, equal to 1? This means if we have for point B only two members framing into it, one of them is 0.5, then the other one must be 0.5. That's it. That easy. Okay, from our previous rule of thumb that we have explained before. Other way, if you do not like this and you want to be sure of what you are doing and to check it, then you can obtain it by KBC over KBA plus KBC. These are the two elements framing into B, which is the same as the denominator in the previous one. However, the numerator here is going to be BC for BC. It is also I over L, right? BC, the far end is fixed. Okay, so we are talking about yes, this is the same. It is going to be I over 2 over 2E, 2I over 20. This means that you're going to find it 50%, which is 0.5. Then it is right. Okay, so now these are the distribution factors. We are going to put it in the table like here and here, 0.5 and 0.5. And then we're going to make the same for, okay, we're going to make the same for point C. So we're going to look to point C. Let's clean everything here. I think that Control E is cleaning. No. Okay, so let's go back, and here this is, everything is cleaned for us. So for the distribution factor for point C, so we're going to start with CB. First, point C, how many members are framing into it? We have CD and we have CB, right? So we have two distribution factors, CB and CD. Okay. Now for CB, okay, CB, we're going to have it KCB over the two of them, KCB plus KCD. CB, the far end here is what? Exactly, fixed. So in this case, we have, this is I, so the distribution or the relative bending stiffness is I over 20. However, the other one, which is the denominator, is going to be KCB, which is already in the numerator, I over 20 plus the remaining span here, which is I over 15. If you calculate it, it is going to be 0.425. As we said before, we have the summation of distribution factor must equal 1. If we have 0.429 here, this means that we must have this value to be 1 minus 0.429. And that's it. No need for the calculation. But if you want to calculate, you can calculate it. And you're going to find it equals to 0.571. Okay, it is equal to KCD over the summation of relative bending stiffnesses. Okay, take care here, it is I over 15 for KCD. Okay, that's it. So we have now the distribution factors for B and C, as you can see it here, and then we can put it in our table. So this is the first step in our table. Take care, this is the first step in our table to put the distribution factors related to the free joints. Okay, so if you are going to ask me why we didn't put distribution factors here, you can answer this because already we have here, it is like 1, there is no other framing joint, so all the moment is going to be taken by this element, so no need to put any distribution factor. Distribution factor here is like 1. Okay, so we are not putting it, it's understood. Okay, let's go to the next step is to find the fixed end moments. The fixed end moments. How we're going to find it? It's very easy. From the back, as we said, inside the back cover of the book, you're going to find span distributed with distributed load 1.5. So the bending moment or the fixed end moments here is going to be 50 here and 50 here. Clockwise, counterclockwise. So this is from the back cover for member AB. We can find these two end moments. Also for frame BC, for span BC, and we have concentrated load, so we can get the fixed end moments easily. For member BC, is going to be PL over 8, if you remember. You can revisit it from the back cover. And for member AB, for distributed load, WL squared over 12, as you can see here. Now we are very skillful in fixed end moments. So 50, which is fixed end moments AB, it is counterclockwise. So it is positive. However, for FEM BA, which is here, it is clockwise, 50. So it is going to be negative. Take care of this. We have explained this many times in the slope deflection method, okay? So we can revisit them again, and you are going to understand what is the meaning of these signs. Okay, for member BC, we have BC and CB. Similar fashion, you are going to get positive 75 and negative 75. They are the same magnitude, but different signs. Same magnitude, different signs and orientation. What about CD? It is 0. There is nothing here. No external forces, no fixed end moments. So fixed end moments for CD or DC, it equals to 0. Right? Okay, so this is the second step, which is or let's assume this is the first step, real step in the table. Before that, it's like a pre-step for the preparation, distribution factors. So in our table now, we have the distribution factors, and the first line in our table is going to be the fixed end moments. Fixed end moments. Fixed end moments, we put it as it is with its sign. Plus 50 here, minus 50 here. This is for fixed end moments AB. This is AB, it is plus. For BA, it is minus. Here it is minus. Similar also. 75 plus minus 75. It is similar here. This is plus, this is negative. And here, there is nothing. No fixed end moments. 0 here. Okay, for member CD. So this is the first step in our table, in moment distribution table, putting the fixed end moments. Now, let's go to the next one, or the next step, which is, I call it, now we are going to choose any join from these two joins, and we are going to make what we call it balance of joint C, for example. We are going to start with this point. What is the meaning of balancing here? In the previous step, we said that we have minus 75 here. It is what? Fixed end moments. This fixed end moments need to be balanced. It is unbalanced moment. What is the meaning of this? Look at this illustration. We have unbalanced moment at joint C, which is 75 due to the fixed end moments, and it is negative. This means that, as you can see, it is negative. So in this case, it is going to be as if that we are applying this moment, okay, this moment on the point or joint C. Okay. This means that there is distributed moments should be developed in order to counteract this this joint, this unbalanced joint. You're going sorry, you are going to ask me why this is negative, and here you are putting it as counterclockwise, which is positive. The answer is, you should answer this, because here we're talking about what? Exactly, joint. However, here we're talking about what? End moment. We said many times that if the end moment is going to be negative, the corresponding joint orientation or sense is going to be positive. So here this is 75, which is counterclockwise or positive. Okay? Take care, as I said many times, the difference between end moment and join moment. So here, as if that we have unbalanced moment with a magnitude of 75. This unbalanced moment needs to be balanced by distributed moments that is going to be developed at joint C from the side of CD and from the side of CB. So there is moments that is going to be developed. These moments is going to be based on the distribution factors that we have. Now let's go back to the table. Now this is only for illustration, but what you are going to do is blind look in the table. So in the table you are going to find minus 75. Then you are going to put in the part of CD and in the part of CB, you're going to find this is negative, then put here negative and negative. And then multiply 75 by 0.429 to give you 32.2, and 75 by 0.571, which is going to give you 42.8. This portion is the amount of moment that is going to be resisted by member CD. And this moment, which is 32.2, it is the amount of moment that is going to be resisted by member CB. Okay? Okay. Now this is what is going to be. We are making balancing, step 2, balancing of joint C. And there is something else we are going to make, which is carry over. It is a carry over. Okay? So now we have balanced the joint by multiplying the distribution factor by the moment magnitude, and we change the sign here to get this positive. Okay, as I said, you are putting the negative, or putting here positive, the opposite, directly. Okay. Okay, so this is 42 also, which is positive, which is going to be here. Okay. Now, we are going to make what? Carry over. As we said, if there is a moment that is going to be developed here, there is moment is going to be carried over by this point. How much? What is the far end fixed? It is, what is the far end here? It is fixed. Then half of the moment that is going to be developed here is going to be carried over here. So if we have 42.8 positive, half of it with the same sign is going to be carried over here, which is 21.4. And similar for this point, or for this moment, which is 32.2 positive, take care of the sign. I always place emphasis upon it. The same sign is going to be here, but half of the magnitude, which is 16.1. Okay, so now this is the carryover. Let me clean it up. So this is, so now we have 42.8, half of it given here with the same sign, 32.2, half of it on the other side. Okay, this is what we call it carryover. So we have balance of joint C and the carryover of point C to the others. So this is the next step here. Now we build up our table, 2 lines in our table now. Let's go to the next step. What is the next step? We're going to make balance for point or joint B. So we leave C as it is and go to B and make another couple of lines here. Okay. Now this is the next step, which is balancing of joint B. We're focusing on joint B. Now here, in joint B, we need to balance it. Balance what? First of all, we have from the fixed end moments, we have minus 50 from the left. We have 75 from the right. This is fixed end moments. And we have 16.1 carried over from point C. Already we have three different moments. They should be balanced because their summation is not 0. What is the summation? We call it unbalanced moment at point B, which is minus 50 plus 75 plus 16.1. It gives us plus 41.1. This is unbalanced moment. It needs to be carried by or resisted by the 2 branches of the point B, which is exactly the right branch and the left branch. Remember, this is the value of unbalanced moment, which is positive. Without thinking, we are going to put it as negative when we are going to put it for the resisting moment. Okay? For the balancing moment, if this is the unbalanced moment is 41, the balancing moment should be with the negative sign. Okay? How much? It's going to be by the distribution factor 0.5. So we have 0.5 times 41.1 and 0.5 times 41.1. Take care. We give the opposite of this positive to make it negative, to get the value here to be negative. So we have negative 20.6 and 20.6. Okay, now this is the first part, which is balancing joint B. Now we want to make carryover. We want to make carryover. So simply, the far end here is fixed, and the far end here it is fixed. So this means that the moment that is going to be developed here, half of it will be carried over here, and half of it that is going to be carried over here. So this minus 20.6, it would give us half of it. It is minus 10.3, and half of it will be minus 10.3 here. Okay, so always remember, carryover moment with the same sign. However, balancing the unbalanced moment with the opposite sign. This is the rule of thumb in the table. You're going to remember it, and I think that if you keep it in your mind and memorize it, you're not going to make any mistakes. Okay? Okay, so this is the unbalanced moment here. This is Alice iteration for you, balancing the joint B. This is the unbalanced moment, okay, which is 41.1. It is on the joint. Take care, this is on the joint. Okay, so this is why it is like clockwise. Okay, clockwise means that it is negative. Actually, it is positive. This is for the beam ends. But here, this is on the joint. So this means there is going to be two moments that is going to be developed in order to resist this 41. Okay, in order to resist 41. They are going to be in the same sense. Okay, they are going to be in the same sense. Both of them in the same sense. Okay, take care, as I said many times, these are end moments. So this means that if we're talking about the joint, they should be reflected on the joint as in opposite direction. Okay, this means that their opposite direction in the joint would counterbalance the joint unbalanced moment. So here it is consistent type of signs. Okay. Okay, so now this is the third step. We have 3 steps up till now. Okay, let's go to the next one, which is going back to joint C. So after balancing point B, we're going to go to joint C again. It is iterative method, as we said. Going between B and C. We're not going to D or A at all. Only we are going to B and C to balance them. So this is balancing of joint C. What will happen here? We have here, count everything here. You're going to find that these are going to give us 0 because already they are balancing an unbalanced moment. So the remaining part that needs to be balanced is what? Only this portion, the 10.3. So this 10.3, which is illustrated here, is going to be distributed between member CD and member CB. Half and half, 0.429 and 0.57. So this 4, take care, 4.4, which coming from is 4.4, 0.429 times 10.3, 0.429 times 10.3. And this amount, 5.9, it equals to 0.571 times 10.3. And then they both positive. Both are positive. They should have the same sign always, which is opposite of the original unbalanced moment. Okay, so we are going to have it positive here. And then this is the balanced joint C. Then we're going to make carry over. So half of it here with the same sign, half of this 4.4 here with the same sign. Okay, that's it. That's it for us. We are going to, now this is point C. Now let's go back again to joint B. And then we're going to balance it, which is this point. We're going to balance joint B. And then we're going to make carry over. Where is joint B here? We stopped already. We were making carry over, which is 2.2 here. Then this 2.2, if you sum up everything here, they are 0. They are like they are being 0 because already this is balanced and unbalanced and balanced moment. So the remaining is 2.2. Then we have distribution factor 0.5 and 0.5. So half of it here, half of it here. Negative, negative, opposite signs. Okay, so 1.1 and 1.1. Then we're going to make the carry over, which is half minus 0.6 here and half, which is minus 0.6 here. So this is step 5. Let's go to the step 6, which is C, going back to point C. Okay, then we're going to look to this amount only to balance it. As I said, all of the remaining up here, they are 0. Their summation is 0, so they are not making any problem for us. Only we want to balance this unbalanced moment, minus 0.6. Exactly, it is going to be 0.429 times 0.6 with the opposite sign, and 0.571 times 0.6 with the opposite sign. It gives us 0.3. Make a carry over, half here. Actually, half of 0.3, it should be 0.15, but we are making like approximation, so 0.2 here and 0.2 here. Take care, the same sign, Then go back to point B again, balance point B, and there is no carryover here, so you stop here. Why should I stop? Because you are working on 0.2. The unbalanced moment is very small, 0.2. You can imagine. So you're going to make the unbalancing or balancing this moment by 0.1 and 0.1 with the opposite sign. And that's it. You stop here. Do not make any carryovers. Okay, stop at balance join B and stop it. When we stop, because it is very trivial now, it's very small. We are stopping at 0.1, which is nothing. So we stop here. Then what should we do? What is the end of this process? We are going to sum up every column at the bottom. So here we have these amount that we have already calculated before. All of them, calculate them and sum them up. It would give us 39.1. And for this column, sum them up, it gives you minus 71.8. For your check, sum this, and it must equal to, yes, 71.7 positive. It must equal to the same magnitude here, but with the opposite sign. Why? Because they must be 0. They should have an equilibrium. Similar here for this point C. Sum everything here. Of course, you are summing the moment. You are not summing up with them the distribution factor. It's out of our summation. So sum them up. You are going to find minus 49. Sum all of them here. They are going to give you 49 with the opposite sign. Sum everything here. You are going to find 24.5. That's it. This is the end moments that we should put. Okay, this is the end moments that we call it the final moments, the final step. Then we're going to put it here. So these are the final moments. We are going to put it in our final member end moments. We have 39.1 positive. Take care, positive means that counterclockwise. It is counterclockwise here. And here it is minus 71.8. For member, we are talking about member AB. So this is moment MBA. So here, minus. It is clockwise. Here, this is clockwise. Then, for this, it is the same. 71.7, it is exactly, it is positive. So counterclockwise. This is minus 49, it is negative. So it is, and so on. Here also this is the same. Let's have it. Yes, it is counterclockwise because it's positive. And the final one is going to be this value, which is 24.5, which is positive, and it is going to be positive. This is what we are ending up the member end moments. This is the member end moments. I hope that you have understood what I have explained here. Now it is time for you to know what is the home assignment. Then this is your home assignment actually. You are going to solve this for moment distribution using moment distribution method. It is very similar to what I have explained before. Work it out and submit it as a homework in your iCampus. Okay, this is the end of this video, and thank you very much for listening to it. And in the same time, I hope that you understand everything that I have explained. Before ending, I want only to recap what I have said here so that you understand the main concept. Okay, so generally what you are doing is making the distribution factors first. So you need to go with the distribution factors. And then distribution factors given, you are going to start with the fixed end moments, which is going to be given from the back cover of the book. You put them here with their signs. Then, after that, you are going to make balance of one joint, look to the joints that are free, and you are going to balance one by one iteratively. One here, one here, one here, one here, and so on. So you start with point C, joint C for example. Any joint will be okay. Just here we started with C. So balance joint C, you are going to find minus 75, which is going to be here. Yes. So which is minus 75. Then we're going to balance it. Okay. After getting the distribution factors, we are going to balance it here and here. This is minus. Then the balancing moment should be positive. And make carry over. Half of it here, half of it here. Because the far end here is fixed. And the far end here is fixed as well. So half of it and half of it. That's it. And then go to the next part, which is joint B. We're going to balance joint B and carry over. Joint B, we have minus 50 and 75 and 16.1. So their summation is 41.1. This makes unbalanced moment here. So it is going to be resisted by both branches. How much resisting? It is going to be based on the distribution factor, half and half. So this 41, half of it is going to be here and half of it is going to be here. That's it. And we're going to make carry over. Half of this value is going to be given to the far end fixed, which is A, and half of this value is going to be given, which is far end is going to be fixed. Okay? And then repeat it again. This is balance joint, yes, this is joint C. Similar, you are going to balance it. As we said, all of these are 0 now. So we don't care about this now. Just we care about the amount that is unbalanced here, coming from the carryover from the previous step. Half of it, not half, 0.429 of it here, and 0.751 of it here, based on the distribution factor. This can be calculated from here. Take care, negative, it should be here, positive and positive. That's it. Half of it will be given here, half of it will be given here, with the same sign. Take care, with the same sign. Then, this is point C. Let's go to point B again. So we are going to balance point B and make a carry over. So the remaining here is 2.2. As I said, all of this, do not worry about it. It is 0. Just we carry this part. We balance this part. So half of it here with the opposite sign, and then carry over. Half here, far end is fixed. You are going to repeat it over and over again, and you are going to find that your table is going to end up with something like this. Sum every column and give it the summation at the bottom of each column, as you can see here. And then this moment is going to be added at each end of the spans that you have. Okay? This is simply what I have done. Okay? This is simply what I have done. Okay, this is the home assignment. I think that you can do it now. This is only not distributed load here. It is concentrated, so take care of this in the fixed end moments. This is concentrated also with half span, or in the middle of the span you can get the fixed end moments, and the distribution factors far end is fixed everywhere. Then you can carry on and work this. Thank you very much, and see you in the next video.